Hi and welcome back to the next lesson in the video series. Today we're going to be talking about standing waves. What is a standing wave? A standing wave is a phenomenon when two waves moving in opposite directions that have the same amplitude and frequency overlap in such a way that the wave seems to only vibrate up and down and not travel sideways. There are many fancy terms for standing waves, and there is this very fancy diagram showing all these different wave patterns based on the number of harmonics that are captured between two endpoints on a string. We're not going to look at this diagram right now, but we're going to look at a FET and see actual movement of the wave on a string, and then we'll come back to this diagram much later. Depending on how quickly a string is vibrated at just the right frequency, a wave will reflect back on itself. Here I will demonstrate the slowest frequency, known as the fundamental, by which a wave for this given length of string will reflect back on itself and not seem to travel side to side, but only vibrate up and down. I will start the FET. As I start the vibration in the FET, you could see that there is a wave bouncing up and down. You may have noticed that it traveled to the right, reflected, and came back. This is the slowest frequency in which this wave produces one antinode. That's one up and one down bump. You see them? Down, and up. So this is called an antinode. And when one antinode from an incoming wave matches an antinode from a reflected wave, these two together create the standing wave pattern that you see here. So this is the slowest wave pattern that can produce a standing wave. Alright, we're going to increase the frequency and we're going to try to produce one full wave on this dashed line or this baseline. Since standing waves are multiples of the wave frequency of the fundamental, we started with 0.48 Hertz. We're going to have to now double that frequency approximately to get a standing wave of the next order of magnitude. As you can see below, I doubled the frequency, and now as I start the generator, I want you to watch the wave travel across the screen to the right, bounce off the clamp, and come back. And then you're going to observe a new phenomenon with two antinodes. Here it goes. Alright, now that looks like a full sine wave, doesn't it? This full sine wave is trapped, one coming in, one reflecting back, on the distance line between the source and the reflection point. I would like you to look at this green node in the middle. This point, the one on the end, the one in the middle, and the one on the other end. These are called nodes. A node is a point that seems to not vibrate while the wave is passing by. Let's check it out. Notice how the green node stays fairly centered on this line most of the time. This second standing wave that's produced on the string is called a second harmonic because it has two antinodes, a trough and a crest. I'm going to increase the frequency now and try to produce three antinodes on the string. Of course, we're going to have to increase the frequency. As you can see, I've increased the frequency to 1.24 Hertz. I'm going to start the generator, and we're going to hope to see three antinodes produced on this string. And there they are. You can see one antinode, a second antinode, and a third antinode. You can also see 1, 2, 3, 4 green nodes. Also notice, trapped on this length of string is 1.5 full waves. Okay, you can see that I've increased the frequency, and I'm going to try to get 2 full waves on the string's length. I have it set in slow motion, this way we can count it easily. Let's begin. So there's your first wave traveling in. Now it reflects and comes back. And now the two waves are opposite of each other. See, it's growing. It'll neutralize. Now you have the full wave once the full wave twice, then the reflection wave once, the reflection wave twice. This is excellent. You could see that this wave has the nodes green and green are on that baseline where they belong. They don't seem to be vibrating up and down, but the rest of the wave around it is. Let's run the simulation just a little longer. Now there is going to be a little bit of wave noise right here. It's not going to be perfectly on the line because this generator right over here is actually moving up and down, so that introduces a little bit of wave noise. But you can see that the standing wave is vibrating up and down, up and down, but not side to side. The points on the line stay on the line. Alright, that was excellent. Let's move on. Here we're back at the physics classroom simulation model, and I have the red and the blue waves just like I had before. And what I'm going to do is line up these waves in such a way that you can see the overlap, the cancellation, and the growth. Here we have the red and blue waves one more time, and I have them lined up in such a way so that when I hit the merge button, you can see that they actually overlap each other almost perfectly. We're going to run the simulation very slowly, and when you see this, purple wave will change because it is the sum of the two waves that are above it. Let's take a look at what happens. Notice as the two waves pass each other, the purple wave begins to oscillate up and down. It doesn't look like it's moving to the side like the red and blue waves are. It's only moving up and down. That's because this wave has equivalent frequencies, wavelengths, amplitudes, and in fact, its velocity is equal but opposite. When the two waves exactly overlap, you can see a higher peak and a lower trough. If you add the amplitudes of two boxes, 2 plus 2 gives you 4. And here you have 1, 2, 3, 4 boxes high in amplitude. And you can look at the negative amplitude, 2 boxes below the baseline, and you have 1, 2, 3, 4 boxes below the baseline. Let's run the simulation and take a look as the waves shift. So here they are shifting away from each other, and just at that moment you can see that the wave has canceled itself out. So the red wave on the top is canceling the blue wave on the bottom, exactly in that position. But if I continue to run, you'll see that they come back together again. So the incident wave, the incoming wave, is reflecting and it is canceling itself out with its own reflection. Let me run this at full speed. And so here is a beautiful example of the standing wave. This wave on the bottom here, this 1 plus 2, this is both waves added together, does not seem to be traveling left or right. The ones above are. The red one is traveling clearly to the right. The blue one is traveling clearly to the left, but the combination of both of these waves seems to create this purple wave, which is standing still. It's only vibrating up and down, up and down. So this is a standing wave. Okay, so let's go back to the beginning slide from the beginning of the video, and we were talking about the standing wave in this very big diagram, which now probably doesn't seem so intimidating at all. So as you saw in the demonstration on the FET, when you have this string, which is represented by this red dotted line right here, you see that you have one antinode, or half of a wave coming in, and then one is reflecting. That was the lowest and slowest frequency. And then I sped it up a little bit, and I was able to get one full sine wave to come in and to reflect back on itself. It has 2 antinodes and now a node in the middle. So that's one full wave. And then I showed you one 2, 3 antinodes, which gave you 1.5 waves. And then they reflect back on themselves. And then finally I showed you 2 full sine waves coming in and 2 full sine waves reflecting back. So that is 2 full waves. 1, 2, 3, 4 antinodes. So an antinode is the crest or the trough. And that's how you count the number of standing waves. Let me show you one question about standing waves that you'd find on a Regents. You have this diagram which shows a standing wave in a string clamped at each end. And they ask, what is the total number of nodes and antinodes in this standing wave? And it's really very simple. The nodes are all these red dots, so it's always the endpoints and the crisscrosses in the middle. And the antinodes are always here. Now you could see, I hope, that this is 1, 2 full waves. So that's the second harmonic, which then reflects back on itself once and twice. And of course, that backwards reflection would oscillate. So this piece would go up and down, but it would not appear that this wave is moving to the right or to the left. Well, that concludes our discussion on interference and standing nodes. Thank you for watching. I hope you enjoyed this video, and we'll see you in the next one.